All right, so let's finish section 15.2. So 15.2, oh, continued. So what have we been working on in section 15.2 so far? We have talked about, we're dealing with unweighted graphs, and we introduced the matrix, which represents the number of edges connecting a starting point or one vertex to the next vertex. And if you recall, when we have this matrix, the convention is that the row is the from and the column is the to. From A to B, it'll be the row representing A and the column that represents B. And we saw that if you raise M to a power, it represents the quantities in the matrix represent how to get from this vertex to that vertex in the power number of steps. So M squared in 2 steps, M cubed in 3 steps, M to the 4th in 4 steps, and so on. If you recall, in chapter 9 on matrices, we had a transition matrix. And the transition matrix represented probabilities of going from one state to another state. Well, if we consider a vertex to be a state, then a transition matrix is very similar to this new adjacency matrix, with one huge difference. If you recall, for a transition matrix, it was the column that was the from and the row that was the to. So it's backwards. And there is a reason for it. It makes things work out the way we want and slightly more advanced complications, situations. But for now, it's important to remember the from and the to for the adjacency matrix is exactly the opposite as the from and the to for the transition matrix. And if you're at a particular vertex and you have these different edges leading away from it, assuming it's a digraph, and if it's not a digraph, then again, each edge is still a possibility, then for a purely random situation, the probability of going via each method, if we assume they're equal, what's called a random walk. A random walk is a very important application. If it's purely random and we can go in any direction we choose, then there's a 1/3 probability of going in each direction. So we can ask the question that we asked in chapter 9, which is which vertex state is the one that you're most likely to be in. And this has huge applications. In fact, on page 704, they talk about Google, the company Google. Essentially, when you do a Google search, you type in, I'm looking for, LeBron James. So there's millions of websites that reference LeBron James. So how do we know what to put first in the Google ranking system and second and third and so on? So essentially, they use graph theory and look at all the links leading to and from pages as edges. So every page is a vertex, and the links on the page would be your directed edges from this page to that page. And then using much more sophisticated graph theory than we're going to do here, they came up with an algorithm that decides what the best web page is if you're looking for that particular subject, and second best and third best, and that's how they rank them. And of course, Google is a multi-billion-dollar industry or company, and web pages in general, extremely important. So we see there's monumental applications of this. So let's do an example, and then we'll jump directly into the exercises. And that will be it for section 15.2. So here's the example. So here's a graph. We have A, we have B, and it's a digraph. So we have a direction there. And then here's C, and the direction is towards B, and there's also a path. Whoops, that is not good. Ugh. Also a path. I can't do this because I go off the page and then my hand slips. Hold on. So something like that. Okay. And then C goes to A, and then A goes this way to F, and in that direction, and also in that direction, and then F goes to E in that direction, and then E goes to D in this direction, and then D goes to F in that direction, and A goes to D, and then D goes to B, and B goes to D, and B goes to D, and D also goes to C. Just double check. It looks like I copied it correctly. Okay. In this graph, vertices A to F represent web pages. So they're using an example similar to what I just spoke about. And the edges indicate links between the pages, right? I might link to you, but you might not necessarily link to me, which is why it's a directed graph, a digraph. For example, page A has links from both C and F and contains links to B, D, F. So A. Construct the transition matrix for a random walk around this graph. It's a random walk, which means every edge is as equally likely as the next one. So A, B, C, D, E, F. Okay. So A cannot go to A. So there's zero chance that A goes to A. A can go to B. And A can also go to D and F. A can go to B, D, and F. So there's a 1/3 chance it goes to B, a 1/3 chance it goes to D, and a 1/3 chance it goes to F. And there's no chance it goes to C or E. B, let's see, B can only go to D, it looks like. So there's a 100% chance if you're in B and you link out, then you go to D. C can go to A or it can go to B. So A and B, 50% chance, half, everything else 0. D can go to B, C, or F. B, C, or F with 0% chance anywhere else. E can only go to D. And F can go to A or E. So F can go to A or E. So that is the transition matrix. Remember, from on top to on the side. So column to row. B, find the steady state probabilities for the network. In other words, where or what is the chance, or what percent of the time am I going to be in A and B and C and so on in the long run? So remember, there are 3 ways of doing this. This is back from chapter 9. So what are the 3 ways of doing this? One way is to set up 6 simultaneous equations, because we have 6 by 6 matrix, and solve the 6 equations. Don't want to do it that way, too much work. Although not really, because most of the numbers are 0. But imagine a scenario where they weren't. Number 2, we can use eigenvectors and eigenvalues, and we can diagonalize the matrix. Again, a lot of work. What's the easiest way? You just take this transition matrix to a power that's high enough until all of the columns are the same. So I'm going to go to my matrix. I'm going to edit. I'm going to use matrix J, a 6 by 6 matrix. 0, 0.5, 0, 0.5, 1/3, 0, 0.5, 1 over 3, 0, 0, 0, 0, 0, 1 over 3, 0, 0, fourth row, 1 over 3, 1, 0, 0, 1, 0, 1, 2, 3, 4, 5 zeros and a 0.5, and then a 1 over 3, 0, 0, 1 over 3, 0, and 0. Okay. And then matrix J, and let's raise it to the, I don't know, 25th power. And by the time I reach the 25th power, I see my screen only shows 2 of the columns because these decimals are big, but I can see that both columns are the same. So we see that the steady state vector is about 0.130, 0.207, 0.109, 0.326, 0.076, and 0.152. And then part C, rank the vertices in order of importance. In order of importance, I guess we'll take the mean, which one occurs the most often. So D, being 0.326, is the only 0.3 that's greater than B. And then let's see, the only 0 is E, so E will be at the end. And then 0.15 is bigger than 0.130, which is bigger than 0.109. So DBFACE would be the order, would be the ranking in order of importance. And you can kind of see from the graph, you know, D has 6 edges attached to it, coming and going. E has 2, C has 3, A has 4, F has 4, and B has 4. So the one with only 2 at the end, the one with 3 next to it, the one with 6 in front, and the one with 4, well, that's not enough information, so we got to do the math. Now, I don't necessarily claim that that's going to be a universal rule across the board, that anytime you have a matrix with more edges in this vertex than that one, this will always be more important. You do have to take into account the directions and what's attached to them and what's attached to those and what's attached to those. Don't do it by hand. The math does it for you. Phenomenal stuff. So now let's go ahead to exercise 15E. And we have 5 questions. So question number 1. For each of the 2 graphs below, find the transition matrix P. So they're changing it from T to P. I don't care what we call it, as long as we know what we do with it. And hence the steady state probabilities by A or by I, considering high powers of P, the way we just did it. And also by solving a system of linear equations. Gross, but let's do it once just to compare the 2 processes to see how much easier one is than the other. So let's do A first. We have a very straightforward matrix. It's not a directed graph. Sorry, not matrix, I meant graph. It's not a directed graph. It's a regular good old-fashioned graph, simple graph, no loops or multi-edges. And let's construct the probability transition matrix, A, B, C, D, A, B, C, D. A cannot go to A, and it has an equal chance of going to B or D, and cannot go to C. B has a chance of going to A, not to itself, but to C or D with equal probabilities. C can only go to B or D with equal probabilities, and D can go to A, can go to B, can go to C, but cannot go to itself. So part I of part A is find the steady state vector by considering high powers. So let's edit a matrix. I'm going to use A. I'm going to use the first one again, 0, 1 over 3, 0, 1 over 3, 0.5, 0, 0.5, 1 over 3, 0, 1 over 3, 0, 1 over 3, 0.5, 1 over 3, 0.5, and 0. This is matrix A, which I'm going to raise to the 25th power. Ooh, the 25th power, they're close and rounding wise. Yeah, we'll round. Looks like the steady state vector, just to be safe, I'm going to do it to the 50th power. And they're still not exactly the same, but much, much closer. Let's just do it for fun to the 100th power. Okay, 100th power, we get a beautiful 0.2, 0.3, 0.2, 0.3 as my steady state vector. All right, so the 25th power and 50th power would be rounded to the right values, but the 100th power gave me the right one straight up. So now let's do it by solving a system of linear equations. Remember what we're looking for. The probability matrix on some state vector gives me that same state vector back. If I transition from the state vector, I get to itself. The steady state vector is the one that I stay in forever once I get there. So we have PV equals V, which means 0, 1/3, 0, 1/3, 1/2, 0, 1/2, 1/3, 0, 1/3, 0, 1/3, and 1/2, 1/3, 1/2, 0, acting on some currently unknown A, B, C, D, gives me that same A, B, C, D under the condition where A plus B plus C plus D has to equal 1. Because it's steady state probability vector. So they have to add to 1. So my first row becomes 1/3 B plus 1/3 D is equal to A. The second one becomes 1/2 B plus 1/2 C plus 1/3 D is equal to B. The next one is 1/3 B plus 1/3 D is equal to C. And then we have 1/2 A plus 1/3 B plus 1/2 C is equal to D. Those are my 4 equations. Personally, I don't like using fractions. So let's multiply everything by 6. Okay, if we multiply everything by 6, this turns into 2B plus 2D, or actually, not only let's multiply everything by 6, but let's get everything to the same side. So negative 6A plus 2B plus 2D is equal to 0. Okay. If we multiply by 6, we have 3B, so minus 3B plus 3C plus 2D is equal to 0. We have 2B minus 6C plus 2D is equal to 0. And then we have 3A plus 2B plus 3C minus 6D is equal to 0. And then don't forget, we have A plus B plus C plus D is equal to 1. Now this is 5 equations and 4 unknowns, but remember the way that these types of problems work, if you recall from chapter 9, one of these equations is redundant, not the last one, of course, but one of the first 4. So I'm going to remove this one, which seems the most complicated. And this gives me the remaining ones. Now, how do I solve a system of equations? Well, nothing says I can't use that with using matrices. So negative 6, 2, 0, 2. Acting on the currently unknown vector A, B, C, D, that gives me a 0. 0, negative 3, 3, 2, that gives me 0. 0, 2, negative 6, 2 gives me 0. And then 1, 1, 1, 1 gives me 1. And then how do I solve for A, B, C, D? Hopefully you recall this. We take the inverse of that matrix and multiply it by 0, 0, 0, 1. So I'm going to go into matrix mode. I'm going to edit another 4x4 matrix. This one is negative 6, 2, 0, 2, 0, negative 3, 3, 2, 0, 2, -6, 2, 1, 1, 1, 1. And then I'm also going to edit another one. This one's going to be a 4 by 1, which is 0, 0, 0, 1. And then I'm going to do that inverse times that. And it gives me, it gives me 0.2, 0.36, 0.2, 0.24. Now that tells me that I made a mistake somewhere. So it's just a matter now of finding the mistake. So let's go back from the beginning very quickly, or actually, I'll pause and I'll look for it. That way you don't have to be bored while I do this, although you should look for it yourself. And I found it pretty quick. Right here in the second second row here, I have 1/2 B plus 1/2 C plus 1/3 D, but it should be 1/2 A plus 1/2 C plus 1/3 D is equal to B. Hopefully you caught that and you weren't just copying me. Okay, and so the change would become here in this row right here, instead of negative, instead of that, it should be 3A minus 6B. And everything else looks good, which means here, these two should be 3 and -6. So now I'm going to go into my edit mode, and that should be a 3, and that should be a -6. And now I'm going to do exactly the same thing, and I do in fact get 0.2, 0.3, 0.2, 0.3. So, mistake. You saw two answers that could not exist simultaneously because they're representing the same answer. You knew your strategy was correct. So what does that mean? You made an error, a typo, you made a mistake. Go back, find it, fix it. No problem. Okay, so now let's do part B. This matrix is a little tougher. First of all, it's a digraph, not a regular graph. We have a loop by A. Here to B, we can go this way, or we can go that way. Here's to C, but we can only go that way. Here's to D, but we can only go that way. Here's to A, and we can only go that way. And then D and B themselves are connected, and we can only go that way. So let's first find the matrix, the transition matrix, A, B, C, D, A, B, C, and D. So let's see. A goes to itself, and it can also go to B. So we have 1/2, 1/2, 0, 0. B goes to A and goes to D. So B goes to A and B goes to D, but not to itself or to C. C must go to B and nowhere else. But D can go to A or C. So 1/2 to A and 1/2 to C, and those are zeros. So that is P. So I'm going to now edit another matrix, 4 by 4. We got 0.5, 0.5, 0, 0.5, 0.5, 0, 1, 0, 0, 0, 0, 0.5, 0, 0.5, 0, 0. This is matrix D in my calculator. I will now raise D to the 100th power. And I have the steady state vector as 0.462, 0.308, 0.077, 0.154. Okay. Now let's do the same thing the other way, which is the matrix acting on currently unknown A, B, C, D has to give me the same A, B, C, D. So my equations are 1/2 A plus 1/2 B plus 1/2 D is equal to A. 1/2 A plus C is equal to B. 1/2 D is equal to C. And 1/2 B is equal to D. So this one, I don't think I need to use my calculator. So here's how I would do it. If 1/2 B is equal to D, that means that, for example, well, what I can do immediately, if that's true, is I can plug 1/2 B in for D. So 1/2 B, I can plug in right there, and I can plug in right there. First equation gives me 1/2 A plus 1/2 B plus 1/4 D is equal to A. Oh, and I missed an A there in the second row. Okay. Second equation, 1/2 A plus C is equal to B. And the third equation is 1/4 B is equal to C. Fourth equation, don't need anymore because I have, oops, this D here should be a B. So 1/2 A plus 1/2 B plus 1/4 B equals A, 1/2 A plus C is equal to B, and 1/4 B is equal to C. Now what I can do is take this C and plug it in there. So my first equation, if I subtract A, I get negative 1/2 A plus 3/4 B is equal, actually, you know what? Let's get all the A's on that side. So I have 3/4 B is equal to 1/2 A. And then I have 1/2 A plus 1/4 B is equal to B. Okay. So this, of course, gives me that 1/2 A is equal to 3/4 B. Which, oh, that's right. We have a redundancy. Of course, we have a redundancy because we have to remember that A plus B plus C plus D has to equal 1. Completely forgot that. So you know what? Let's go back. My apologies. And let's throw that in here. First, let's get rid of this one, which will be our redundant one. And then we'll throw in A plus B plus C plus D is equal to 1. So let's try this again. So I'm going to plug in B into there, C into there, and D into there. So that gives me A plus 1/2 A plus C plus 1/2 D plus 1/2 B is equal to 1. You know what? Sometimes you just do things a couple times and just change your mind. Let's just do it the matrix way. I mean, I can finagle these, but it's just so much more systematic. So what I have now, the first equation becomes 1/2 A minus 1B plus 1C with no D's equals 0. The second one comes negative 1C and 1/2 D equals 0. The third one becomes 1/2 B and negative 1D equals 0. And the last one becomes A plus B plus C plus D is equal to 1. So let's plug it into the calculator. Edit, new matrix, 0.5, negative 1, 1, 0, 0, 0, negative 1.5, 0.5, 0, negative 1, 1, 1, 1, 1, and take that matrix inverse and multiply it by 0.0001. And I do in fact get this. Did I erase it? Oh no, there it is. I still get 0.462.308, 0.077.154. So I do get the same answer. Both ways work. So we have success. Again, notice using your matrix to a high power is without question the fastest way. Question 2. In an experiment on artificial intelligence, a robot is put in a maze which has 6 rooms. So here is the maze. There's room A in the top right. Looks like there's a doorway, 2 doorways out. This one goes to B. And there's 2 more doorways out. The lower doorway goes to C. The upper doorway goes to room D. Upper one above that is E. And then here we have F. Each of the rooms has gaps in the wall connecting it to adjacent rooms. A, draw the maze as a graph, with the vertices representing the different rooms and the edges representing the gaps between rooms. Again, you should always be doing this yourself first. So here's A, here's B, and we have an edge from A to B. Here's C, we got an edge from B to C. Here's D, which connects to C and also connects to B, and also connects to E, and also connects to F. Now E connects to A, and F connects to E, and also F connects to C. Okay, looks good to me. The robot moves randomly, and once in a room is equally likely to leave through any of the gaps. So we have a random walk. So, well, since we know it's a random walk, that means we can write down the transition matrix. So A, B, C, D, E, F. A, B, C, D, E, F. Please go ahead and do that. I'll do it here. C, B, D, F. D, B, C, E, F. B, C, E, F. E, A, D, F. And F is C, D, E. Okay, so that is the transition matrix. C. If the robot begins in room A, what is the probability it is again in room A after passing through 4 gaps? So as always, you should be thinking about this one and trying it yourself. So I'm going to make a 6 by 6 matrix, 0, 1 over 3, 0, 0, 1 over 3, 0, 0.5, 0, 1 over 3, 0.25, 0, 0, 0, 1 over 3, 0, 0.25, 0, 1 over 3, 0, 1 over 3, 1 over 3, 0, 1 over 3, 1 over 3, 0.5, 0, 0, 0.25, 0, 1 over 3, 0, 0, 1 over 3, 0.25, 1/3, and 0. So this is what I'm calling matrix G. So how do I do this? I take matrix G, raise it to the 4th power, which represents 4 steps. So the probability of A to something to something to something to A is approximately 0.204. Roughly a 20% chance. A, 1, 2, 3, yeah, 1, 2, yeah, I see a few ways of doing it. A, B, A to B to A to B to A, or A to E to A to E to A. So 1, 2, 3, 4, 1, 2, 3, 4, or A, B, D, E, A, or A, E, D, B, A. That way, there's four ways. Now, if you didn't have this matrix and you didn't have this approach, I don't see any way that you could have divined that answer. So, these just really, really make these problems easy. So D, find the 2 rooms which are most likely to be visited by the robot. Find the 2 rooms which are most likely to be visited by the robot. So as always, try to do it yourself first. So I did the, I raised it to the 100th power. And there's one which is clearly the one that it's in the most. But the problem is that the other ones are equally likely. So this is question 2D. It says B and E. Well, let me check my matrix because, let's see, did I get the last one right? It's telling me I did the last one wrong. So let's check my matrix. First of all, let's check my graph. A goes to B and E. B is ADC. C is just B and D. Ooh, there it is. C doesn't go to F. Uh-oh, sorry about that, guys. C does not go to F, which means those are both 1/2. Sorry, mea culpa. So let's edit my G matrix and C, the 3rd column, so that should be a 0.5, and that should be a 0.5, and that should be a 0. So let's try this again. G to the 100th power. And, oh, that's, sorry, I want G to the 4th power first, sorry. G to the 4th power. And that gives me not 0.204, but that gives me 0.213. Now, when I look at G to the 100th power, now the 2 rooms that it's in the most are clearly D at a 0.241 probability and B at a 0.203 probability. And then E. Oh, well, it says determine the percentage of time that the robots will be in each of these rooms, and I just answer that. B and E, it says 18.75% of the time. Now that doesn't make any sense. That does not make any sense at all. No, D is, I mean, of course, I have made mistakes before, but I'm pretty sure I corrected it. Let me double check. So C goes to D and B, D goes to B, C, E, F. E is ADF, and F is, oh no, F is D and E. Okay, no, so that's good. Let's check my matrix. 0, 1/2, 0, 0, 1/2, 0, 1/3, 0, 1/3, 1/3, 0, 0, 0, 1/2, 0, 1/2, 0, 0, 0, 1/4, 1/4, 0, 1/4, 1/4, 1/3, 0, 0, 1/3, 0, 1/3, 0, 0, Yep, another mistake. Hopefully you're catching this. F only goes to D and E. I don't know what I was thinking here. F goes to D and E. One of these days, I will have to redo all these videos and correct all my mistakes. But for now, I'll just have to apologize. So 0.5 and 0.5. So again, matrix G to the fourth power. And now I get, hopefully this is correct, 22.2%, 0.222. And when I raise G to the 100th power, I get, yep, okay, there we go. Fair enough. 18.75% of that one and 18.75% of that one. And the only thing I can say is check your work. It does take a little time, which is why I'm trying not to, because these videos are long enough. And what's the result? Making mistakes that are easily catchable and taking longer. So I have learned something in the process. All right, question 3. Until I make the same mistake next time. The following diagram shows 4 websites. We have website A, we have website B, we have website C, and we have website D. The arrows indicate a link from one of the pages to another. So C goes to A, C has a link to B, D has a link to C, B and D link to each other, A and B link to each other. Checking, 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 checking. Okay, A, write down the transition matrix to represent a random walk around the graph. So go ahead and do it. A, B, C, D, A, B, C, D. So A does not link to itself. A only links to B. So if you're at A, you're only going to go to B. If you're at B, you can go to A or D, but you can't go to itself, and B does not go to C. C does not go to D or itself, but it does go to A and B. And D certainly does not go to A. And D does not go to itself, but D goes to both B and C. Okay, so that's a transition matrix. B. Show that it is not possible to link from B to C in exactly 3 links. Show that it's not possible to go B to C in exactly 3 links. And write down 2 other connections that are also not possible using exactly 3 links. So I'm going to edit a matrix 4x4, 0, 0.5, 0.50, 1, 0, 0.5, 0, 0, 0.5, 0.500. Okay, so 3 links it said, so we're going to raise A to the 3rd power. And we have a 0 in 3 locations. So T cubed equals 0, non-zero, non-zero, 0. I'm putting these dashes to indicate that I really don't care about them, but I have 3 zeros. So impossible to go A to A to D, or B to C in 3 links. Okay, C. And by solving for linear equations, find the steady state probabilities. So they want us to do it that method. Hopefully the math won't be too hard. Let's take a look. A, B, C, D gives me A, B, C, D. First one gives me 1/2 B plus 1/2 C equals A. A plus 1/2 C plus 1/2 D is equal to B. 1/2 D is equal to C. 1/2 B is equal to D, and A plus B plus C plus D is equal to 1. Let's throw out that one, which is the most complicated. Okay, so let's take a look. A, I'm going to replace with 1/2 B plus 1/2 C. B and C I'm going to keep for now. And D, I'm going to replace with 1/2 B. But this will give me an equation involving B's and C's. Yeah, screw that. Instead, let's go ahead and just do it the way we normally do it. Negative 1A plus 1/2 B plus 1/2 C and 0 D's gives me 0. No A's, no B's, negative 1C and a 1/2 D gives me 0. No A's, 1/2 B, no C's, and a negative 1D gives me 0. And one of each gives me 1. Okay, so matrix edits 4 by 4, negative 1, 0.5, 0.50, 0, 0, negative 1, 0.5, 0, 0.50, negative 1, 1, 1, 1, 1. So that's matrix B, which I'm going to inverse and multiply by this other one that I already have there. And that gives me 0.263, 0.421, 0.105, and 0.211. I'm going to check the back before we go on, just to make sure I didn't do anything really, really dumb, which I'm known to do. This is C. So let's take a look. Is 5/19 that number? Yes. Is 8/19 that number? Yes. Is 2/19 that number? Okay, yeah. So I have the answers that they have there. And then, so that was, this is part C. And we're looking for the steady state probabilities. And then the proportion of time that a person following random links will be on site B, that's just going to be 42.1% of the time, which is just the answer in part B. D. Based on this information, write down the order in which the sites might be listed by a search engine, giving the one with the largest state probability, largest steady state probability first. B will be before A, will be before D, will be before C. All right, question number 4. Within a large social network, links can be created from one person's page to another. A small group of people share links according to the table below. Antoine, Belle, Charles, Don, Emil, I don't know, and Francis. These are the 6 people. A shares links, I'm not even going to say their names, to B, C, and E, B to A and C, C to A, B, and D, D to E and F, and E to A and D, and F to D. Google is also part of the network and friends with all of those listed. Google is also part of the network and friends with all of those listed. For example, from Antoine's page, it is possible to link directly to the pages of Bell, Charge, and Emil. So from Google's page, we can go to either A, B, C, D, E, or F. But does that mean that we can go to Google from all of them? Oh, sorry, not Google, George. I misread it. George is also part of the network and friends with all of those listed. He decides, okay, so he's friends with, okay, does that mean that they can link to him or that he can link to them? He is friends with all of those listed. Does that, I don't know how to interpret that. Does that mean he can link to them or that they can link to him? So well, let's hold off on that for a second based upon what they won in part A anyways. So it says George is also part of the network and friends with all those listed. He decides to visit the pages of each of them in the following way. Having chosen a starting page, he will then move to another page by choosing randomly from the list of possible links on his current page. Okay, so we don't actually need George. George can just access all of them, but he's not part of the network, or he's not part of the problem. Okay, so show the information from the table in a directed graph. Okay, so here's A. Again, doing this yourself. Here's B, here's C, here's D, here's E, and here's F. A can go to B, A can go to C, and A can go to E. B can go to A, and B can go to C. C can go to A, C can go to B, and C can go to D. D can go to E, and D can also go to F. E can go to A, and E can go to D. And F can go to D. Okay, so that's the graph. That's A graph. B. From the graph, explain why it is not possible for George to visit each of the friends' pages in the first 6 pages he looks at if he begins on Antoine's page. Why it is not possible to visit each in the first, okay, is it possible to get to everyone in exactly 6 links? If you start on A, where can you go? You can go to B, you can go to C, and you can go to E. Here we go. Ready? If you go to E, then since the only connection to E is F, the only way you're going to get to F in exactly 6 links is if you don't come back, you don't do anyone twice. You don't do E, leave, come back to E again. So E would have to go to F immediately, but F can only go back to E, so that one's out. That's not possible. Now, if you go to B, then the only possibility from B is either A, which is redundant, or C. And if you go to C, then you can go to D. But here's the problem. D can only go to E or F, right? Oh, wait a second. A to B to C to D to E. Sorry, D. D can only go to E or F at this point. Where's E? No wonder, he's over here. Sorry, let's go back to this first one. If A goes directly to E, okay, we'll get back to that one. I made a mistake. So let's continue on the first path. A to B to C to D, and then D to either to E or to F. But E cannot go to F, and F cannot go to E. So that's not possible. And if we go to C, then we either go to B or not B. But either way, you're stuck because B can only go to C or A. And if we don't go to B and we end up on the D side, the only way to get back to B is through C, which is a repeat. And if A goes to E, then the only option after that is to D. And either we go to F or not F. And if we go to F, we got to come back through D. And if we don't go to F, we got to come back through D. So yeah, it's not possible if we start at A to visit all 6 of them in exactly 6 links. C. Determine whether it's possible to visit each of the friends pages in the first 6 visits if it begins on another page? If so, give a possible order, and if not, say why not. So what if we started somewhere else? What if we started somewhere else? Where could we start? Well, I'm going to start at F, because if I start at F, I can go directly to D. And then from D, I can go to E. I can go to A. I can go to B. I can go to C. So yes, there's more than one possible order, because over here I could have done C then B as well. Let's see which order they have in the book. They have yes, if you begin on Francis' page, Francis, Dawn, F, D, E, A, B, C, although technically A, C, B works too. So yes, you can do it. Okay, D. Construct a transition matrix for your graph. So it's going to be a 6 by 6, A, B, C, D, E, F, A, B, C, D, E, and F. Okay, so let's take a look. From A, so first of all, nothing links to itself. Okay, A does not go to F. A does go to E. A does not go to D, but A goes to B, to C, and to E. So B, C, and E. B goes to A and C. B goes to A and C. C goes to A, B, and D. A, B, and D. D goes to E and F. E goes to A and D. And F only goes to E. Okay, so that is my transition matrix. Okay, now George begins by visiting Antoine's page. Find the probability he's back on Antoine's page after visiting 5 other pages. So A to something, something, after visiting 5 other pages. So we're looking for A, 5 other pages, or after visiting 5 further pages. In other words, I think what they want is the probability that we started A, and then the 5th page after that is A again, which is a total of 5 links. So I'm going to edit I'm gonna make a 6 by 6 matrix, 0.5, 1 over 3, 0.5, and 0, 1 over 3, 0, 1 over 3, 0, 0, 0, 1 over 3.5, 0, 0, 0, 0, 0, 0, 1 over 3, 0.5, 0, 1 over 3, 0, 0.5, 0, 1, 0, 0, 0.5, 0, and 0. So that's matrix A to the 5th power. So this gives me 0.201, so about 20.1% chance that I am back there after 5 further pages, which is not what he has there. Let's check my A again. Let's check my matrix. 0, 1/3, 1/3, 0, 1/3, 0, 1/2, 0, 1/2, 0, 0, 0, 1/3, 1/3, 0, 1/3, 0, 0, 0, 0, 0, 0, 1/2, 1/2, 1/2, 0, 0, 1/2, 0, 0, 0, 0. Ah, I made a mistake here. F and D, not F and E. So let's fix that. edit. That should be a 1. That should be a 0. And let's do the same thing, a to the 5th power, and we get, yes, the same thing they get, which is approximately 0.131. This matrix stuff's so easy to make a typo if you are just not too careful, which I haven't been. That's my bad. So 0.131, 13.1%. F. Determine the probability that he visited the pages in the order Antoine, Bell, Charles, Don, Emil, Antoine. Well, we don't need a calculator for this. Think about it. A to B, we know, has a 1/3 chance of occurring. B to C is a 1/2 chance of occurring. C to D is a 1/3 chance of occurring. D to E is a 1/2 chance of occurring, and E to the A is a 1/2. So because we have a sequence of events that are independent of each other, we would just multiply, and the probability would be 9, 18, 36, 1/72. Yeah, 1/72. G. George continues moving through the web pages in the same way for a long time. Find which page he's likely to visit the most and the least. Okay, no problem. Just take the matrix A, the 100th power, and the most highest probability would be D with a 27% chance, and the least likely would be B with a 10% chance. Does that seem reasonable that the least likely is B? Well, B is off on the side. I'd actually think that F would be the least likely, but not according to this. So let's check it again because, yeah, the most likely is D and the least likely is B. So this is great because it shows you that just because it has the fewest edges or it's off to the side for whatever reason that you think it might be the least, trust the math and then double check your work to really trust the math. Okay, and finally, question number 5. Explain why the long-term probabilities for this graph will not be independent of the starting position. So here's an interesting question. We have A and we have B, and B goes to A. C's up here and C goes to B. F is down here, which goes to B and back. And here's D, which goes to D, and D and C go both ways. And here is E. So again, A, explain why the long-term probabilities for this graph will not be independent of the starting position. And in other words, it makes a difference where you start. Well, if you start at E or you start at A, you'll be there forever because E and A, you can't leave. Whereas if you start at B, C, D, or F, then things are different, of course, because you have the opportunity to move around. So long-term probabilities depend on where you begin. Okay, what do they say is their answer here? 2 states are absorbing states, which means once you're there, you stay there. And the probability of each of them, of entering each of them will depend upon the starting position. It's exactly what I said. Lovely. Okay, A and E are absorbing states. An absorbing state is one, once you're there, you stay there. B. Write down the probability that a random walk would end at vertex A if it began at vertex B. Now, you might think here that if you begin at vertex B, that you are guaranteed to have a 1/2 chance of ending at A. Why a 1/2 chance of ending at A? Well, if you're a B, you can go A or F. So 50-50. But if you go to F, that does not mean that you can't eventually get back to A. So it's going to be more than 50%. It's going to be the 50% if you go immediately, plus the likelihood of going back to A somehow via going through B, and so on. Does that make sense? Hopefully that makes sense. But is it possible to ever end up anywhere else? So let's say you go to B. Well, you can go to A and you're done. Or you can go to F. Now, F can go back to B, in which case we're basically repeating the process again. So I'm just going to say ... meaning whatever else we conclude everywhere else will be the same conclusions up there. Where else can F go besides B? Well, nowhere. It can't go anywhere else. So F must go to B, which goes to A and we're done, or F, which goes to B, which goes to A and we're done, or F, and so on. In other words, no matter what, you will eventually get to A, no matter what, which is pretty cool, I think. Part C. Find the transition matrix for the graph. Okay, well, let's take a look. We have A, B, C, so 6 by 6. A, B, C, D, E, F. A, B, C, D, E, F. A can't go anywhere. Once you're in A, well, I guess once you're in A, you stay in A. So this has to be a 1. Because if you're in A, your next state has to be A as well. There's no loop by A to indicate that you're remaining there. But remember, to be a valid probability transition matrix, every column has to add to 1. So if they were all zeros, it makes no sense. It's not a transition matrix. So if you look at it from a graph perspective, then yes, there's no loop there. It should be a 0. There's no edges. But if you look at it from a probability perspective, the vertices are states. I'm in one state, the next day I'm in another state, the next day I'm in another state, and so on. So if you're in A, the next day you are guaranteed to be in A because you cannot leave. So B can go to A, or it can go to F. So the 1/2 chance of going to A, a 1/2 chance of going to F, and you can't go anywhere else. C can go to B, D, or F. B, D, or F. D can go to E, it can go to C, E, or F. C, E, or F. E can't go anywhere but E. E stays in E, and F only goes to B. So let me check that. That's what I have. I no longer even trust myself with how many mistakes I've made in this video. So 15, we have 1, 1/2, 1/2, 1/3, 1/3, 1/3, 1/3, 1/3, 1/3, 1, and 1. Okay. And then, oh, that's actually D. I skipped C. See, another mistake. Ooh, okay. So what is C? If X is the number of walks it takes for the walk to reach, oh, this is a nice problem. Okay. So X is the number of walks it takes. X is defined as the number of steps to go from A to B. We want to find the expected value of X. How many steps do we expect it to take on average? So this one is not straightforward. Got to think about it. What's the minimum number of steps it requires to go from B to A? Did I say from A to B? I meant from B to A. Another mistake. From B to A. Well, it could take one step, and the probability of that occurring is 1/2. Remember how we calculate expected values? Every possible number of steps times the probability of that occurring. So there's a 1/2 chance of going from B to A in one step. What's the next number of steps to go from B to A? Well, it can go to B to F to B to A. That's 3 steps. And what's the likelihood of that occurring? Well, it's 1/2 of the remaining 1/2. So that's a 1/4 probability of going in 2 steps. 1/2 to go to F and then 1/2 to go to A. Plus 5 times 1/8. Plus 7 times 1/16, and so on. We have a pattern here. The question now becomes, is there a way to get a nice number for this pattern? So let's see if I can do some nice, ingenious manipulation here. So what do I have here? I have 1/2 plus let's see. Actually, there's a nice trick of doing this, which is a little more sophisticated. So this way is a little complicated. So let's do it in a slightly different way, which is as follows. We'll see if this works. The expected value of X is equal to 1 times, I got to think how I want to do this. I saw this years ago. Very, very cool technique. Basically, the expected value of X is equal to 1 times 1/2 plus. Now, suppose you don't go to A immediately. Then it's going to be 2 steps to go back to B plus, and now we're back to where we started. So plus E of X times 1/2. I think this is it. 1 step, 50% chance. Or 2 plus, and you're back to where you started. Let's see if this works. Let's see if this works. E of X equals 1/2 plus 1 plus 1/2 E of X. So if I subtract 1/2 E of X, I get 1/2 E of X equals 3/2, in which case E of X is equal to 3. And that is the answer. E of X is equal to 3. That was not easy. Nothing I would expect a student who's learning this for the first time to be able to do on their own. I don't know what method they were expecting, because this original sum here, I don't really see a simple way of evaluating. So I'd be surprised if they want you to do it that way. I'll have to look into that. But yeah, that one was not at all easy. So D was find the transition matrix, we just did, and now we have E. By evaluating high powers of the transition matrix, find a long-term probability of being at vertex E if you begin at vertex C. So let's plug in, let's edit this. This is a 6x6. 1.500000 1 over 3 0 0 0 1 0 0 0 0 1 over 3 0 0 0 0 1 over 3, 0, 0, 0, 0, 0, 0, 1 over 3, 1, 0, 0 0.5, 1 over 3, 1 over 3, 0, and 0. So this is matrix A. So matrix A to the 100th power. So the matrix A to the 100th power gives me a steady state vector of 1, 0, 0, 0, 0, 0. Let me first make sure I inputted A correctly. I did. So it says, by evaluating high powers of the transition matrix, find the long-term probability of being at vertex E if you began at vertex C. So if you do A again to the large power, final, okay, so when I do it to a very high power, I just get 1 in the top left, and zeros everywhere else, unless, matrix A, or do I? Actually, I don't get the same thing in every one. So if you begin at vertex C, so let's go to the third row. Oh, actually interesting. I get 0.125. Probability equals 0.125. It's not the same in every column. And you know what? If you recall, you only get the same in every column if it's a regular matrix. So apparently this is not a regular matrix because I do get 0.125 and the book gets 0.125. So not being a regular matrix, we don't get the same in every column. So we get 0.125. Okay, so I do apologize again for my typos. I'll try to be more careful in the sections that come, especially as it gets a little more complicated. But that's it for unweighted graphs. So for unweighted graphs, we really only have this concept of the adjacency matrix and powers of the adjacency matrix to compute probabilities using the relationship between the matrix and the transition matrix. And that's it. That is, and the number of walks. How many ways can I get from here to there in a number of steps? It's all about powers of either the adjacency matrix or of the transition matrix. In the next section, 15.3, we're going to move on to weighted graphs. And there are 3 sections on weighted graphs. So I'll see you there. Bye.